Hello and welcome to ArXiv Preprint Server Daily, your source for the latest in artificial intelligence research. Today's focus is on the dynamic field of computer vision. A selection of preprints from the ArXiv, all submitted on May 4, 2025, will be examined. The goal is to provide a digestible overview of current trends, challenges, and breakthroughs shaping how machines perceive and interact with the visual world. This presentation surveys recent computer vision preprints, focusing on image understanding and interpretation. It provides an overview of key themes, findings, and methodologies, exploring the future direction of AI vision systems. Computer vision is more than just enabling computers to see. It's about enabling them to understand and interpret the visual world in a way that rivals, and in some cases surpasses, human capabilities. It's a branch of AI dedicated to training machines to extract meaningful information from images and videos. This involves a diverse set of tasks, such as identifying objects, recognizing faces, understanding scenes, and tracking movement. Computer vision is AI dedicated to understanding the visual world. Tasks include object identification, scene understanding, and tracking. It is a driving force behind self-driving cars, medical imaging, and security, with virtually limitless applications across industries. As we delved into these papers, several prominent research themes surfaced, offering a glimpse into the active areas of investigation within computer vision. A key theme emerging is image enhancement and super resolution. The goal here is to improve the quality and detail of images, particularly in scenarios where the original data is limited or degraded. For example, the paper by Zhang et al. Addresses the challenge of enhancing hyperspectral images, which capture information across a wide spectrum of light, but often have low spatial resolution. A key theme is improving image quality, with Zhang et al. Addressing the enhancement of hyperspectral images. The focus is on applications in remote sensing and environmental monitoring, enhancing image fidelity and spatial resolution. Another critical theme is 3D scene understanding and neural rendering. This encompasses reconstructing 3D models from images or point clouds and then generating realistic renderings of these scenes. Advancements in neural radiance fields, or NeRFs, are central to this theme, as illustrated by the work of Ivashechkin et al. On rendering sign language with Gaussian splatting in Mi et al. On learning heterogeneous mixtures of scene experts for large-scale neural radiance fields. 3D scene reconstruction and realistic rendering is crucial. Ivashechkin et al. Use Gaussian splatting for sign language. Mi et al. Work on large-scale neural radiance fields. NeRFs represent scenes as continuous functions. Object-centric learning and scene decomposition is a related, yet distinct, research area. This theme is dedicated to developing methods that can automatically identify and segment objects within a scene, often without relying on explicit labels. This allows systems to understand the composition of a scene and the relationships between different objects, as exemplified by the paper from Kuchiksozen et al. Object-centric learning involves automatically identifying objects without explicit labels. It enables understanding scene composition and object relationships. Kuchiksozen et al. Work on scene decomposition, enabling more granular scene understanding. Vision language models and multimodal understanding represent another significant theme. These models are designed to bridge the gap between visual and textual information, enabling machines to perform tasks like image captioning, visual question answering, and detecting manipulated images. The paper by Wang et al. On handling imbalanced pseudolabels for vision language models and the work of Peng et al. On face forgery detection using vision language fusion exemplify this trend. Vision language models are used for multimodal understanding. Wang et al. Address imbalanced pseudolabels. Peng et al. Focus on face forgery detection using fusion, combining visual and textual inputs for various tasks. Looking at the reported findings, several noteworthy results emerge. Zhang et al.'s work on hyperspectral image super resolution demonstrates significant improvements in aligning and fusing information from RGB images, resulting in sharper and more detailed hyperspectral images. This has direct applications in remote sensing and environmental monitoring where detailed spectral information is crucial. Ivashechkin et al.'s Sign Splat paper showcases a novel approach to rendering sign language using Gaussian splatting, achieving state-of-the-art performance in capturing the subtle nuances of hand and facial movements. Key findings include Zhang et al.'s sharper hyperspectral images via RGB alignment, Ivashechkin et al.'s realistic sign language rendering with splatting, Schuin et al.'s RTV bench highlighting the need for better architectures, Dalmas et al.'s memory-efficient uncertainty calculation for MRI images, and Shane et al.'s segment anything model adapting to RGB thermal tasks. Across these papers, several common methodologies are used. Convolutional neural networks, or CNNs, remain a cornerstone. These networks excel at automatically learning spatial hierarchies of features from images, making them highly effective for tasks like image classification and object detection. However, CNNs can be computationally expensive, and may struggle to capture long-range dependencies in images. Transformers, originally developed for natural language processing, have become increasingly popular in computer vision. Key methodologies include convolutional neural networks, or CNNs, which remain foundational. Transformers are used for capturing global context with attention mechanisms. Neural radiance fields, or NeRFs, are used for representing scenes as functions. Gaussian splatting enables real-time rendering of 3D scenes. Optical flow estimates motion in video sequences. To illustrate these research trends in more detail, let's examine 3 selected papers. First, we turn to Zhang et al.'s paper titled, Unaligned RGB-Guided Hyperspectral Image Super Resolution with Spatial Spectral Concordance. The objective of this research is to improve the spatial resolution of hyperspectral images using readily available, high-resolution RGB images as a guide. Hyperspectral images are valuable because they capture data across a wide range of the electromagnetic spectrum, providing detailed information about the composition of materials. This spatial spectral concordance HSR framework from Zhang et al. Uses 2-stage alignment and feature fusion to improve hyperspectral image resolution with RGB guidance. The 2-stage alignment module uses a fine-tuned optical flow model. To overcome this challenge, the authors propose a spatial spectral concordance hyperspectral super resolution, or SSCHSR, framework. This framework has 2 key components: a 2-stage image alignment module and feature aggregation and attention fusion modules. The feature aggregation module uses an iterative deformable feature aggregation block. The attention fusion module uses 2 spectral-wise attention blocks. Experimental results on natural and remote sensing datasets show that SSCHSR outperforms other approaches in both quantitative and qualitative evaluations. The feature aggregation module uses an iterative deformable feature aggregation block. Feature fusion module uses 2 spectral-wise attention blocks. It outperforms other methods on natural and remote sensing data. Next, we consider the paper by Ivashechkin et al., titled, Sign Splat. Rendering sign language via Gaussian splatting. The main objective of this study is to develop a high-fidelity method for rendering sign language, focusing on capturing the subtle and complex motions of the hands and face. The authors propose a framework that uses sequence data and constrains mesh parameters to build an accurate Gaussian splatting model from a few views. They include regularization techniques applied to the Gaussian parameters to reduce overfitting and rendering artifacts, which are common when working with limited data. Sign Splat, by Ivashechkin et al., uses Gaussian splatting for high-fidelity sign language rendering. Regularization techniques reduce overfitting. An adaptive control method prunes splat points on the mesh surface. Neural machine translation approaches are used for sign stitching. State-of-the-art performance is achieved on sign language datasets. Finally, we consider the work of Schuin et al. RTV bench. Benchmarking MLLM continuous perception, understanding and reasoning through real-time video. The paper addresses the gap in benchmarks that can properly evaluate the ability of multimodal large language models, or MLLMs, to continuously perceive, understand, and reason in dynamic real-world environments. To solve this problem, the authors introduce RTV Bench, a new benchmark specifically for MLLM real-time video analysis. Schuin et al.'s RTV Bench is a new benchmark for MLLM real-time video analysis. It is built upon principles of multi-timestamp question answering, has a hierarchical question structure, And simply making models bigger, higher frame rates doesn't improve performance. This emphasizes the need for architectures for video stream processing. In conclusion, the field of computer vision continues to show tremendous growth and innovation. Researchers are constantly pushing the limits of what's possible in areas like image enhancement, 3D scene understanding, and multimodal learning. While we see impressive progress in solving complex problems and developing new technologies, significant challenges persist. Future directions in computer vision research include an emphasis on efficient algorithms and hardware acceleration. Development of models must be robust to real-world imperfections, with continued progress expected in multimodal learning, focusing on improving generalization and interpretability. The content for this presentation was synthesized using GPT and Gemini models, Gemini 2.0 Flash. The TTS synthesis was generated using Google's text-to-speech. Images, which are not included in this output, were generated using Stable Diffusion. The generated content was reviewed and edited by a human expert. Computer vision is a rapidly evolving field. Computational cost and robustness remain key challenges. Continued advancements are expected in multimodal AI systems. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from ArXiv preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights.